There are three main objectives in this project. The first is to analyze the possibility of confidentiality breach. The second is to develop machine-specific and machine-independent countermeasures against confidentiality breach. And third is to utilize these analog emissions to detect or predict breach in integrity and availability. The digital process chain of additive manufacturing can be attacked from various points. However, we are mostly interested in side-channel attacks. There are various consequences of this particular attacks being carried out from various points. However, we'll try to analyze how the side-channel attack can affect the confidentiality of the system, and it can at the same time be used to detect integrity and availability vulnerabilities in the system. There has already been various research efforts to highlight the vulnerability of 3D printer to integrity and confidentiality attacks. As mentioned earlier, in first objective, we'll try to analyze how much information is being leaked from various side channels. A 3D printer can give off various analog emissions, and side channel analysis utilizes the physical weakness of this particular system to leak the cyber domain data to reconstruct the cyber domain data. For example, the 3D printer can behave as an acoustic side channel. Let us hear the 3D printer play music which has been fed by the cyber domain. Based on these side channels, an attacker could easily create an attack model by gathering this emission and trying to reconstruct the cyber domain G code by using various learning algorithms. In order to reverse engineer the G code from the side channels, an attacker would require various kinds of regression classification models to predict various portions of the G code. In our attack model, we created various classifiers to determine the axis movement of the 3D printer, whereas we created regression models to predict the speed and distance of movement by the 3D printer. By just using analog emission in our first project, we were able to reconstruct key-like structure easily by just listening to the emissions. To extend this work, we also analyzed multi-channel side channels and used various forms of test objects to see if we could reconstruct these objects as well. We measure the success rate as the learning model's capability to accurately predict the points in XY plane. As you can see in the figure, as deviation in prediction increases, the success rate increases, whereas the critical range is the reason where the deviation is as minimum as possible. By utilizing the multi-channel emissions, we were able to reconstruct the original object as shown on the right. As you can see, we were able to reconstruct various details of the original 3D object. In our second work, we developed various mission-specific and mission-independent countermeasures against this confidentiality breach. In our work, we tried to create a secured computer-aided manufacturing tool such as slicing and toolpath generation algorithm that obfuscates this G and M codes being sent to the 3D printer and makes the reverse engineering process harder. We then tested our algorithm against various benchmark models. We found out that in every case we were able to reduce the mutual information using our secure computer-aided manufacturing tool. Moreover, the average drop in mutual information for these benchmark objects was 24.76%, with the average increasing printing time with just 0.58%. In our third work, we utilized these analog emissions to detect integrity attacks. Since additive manufacturing is a cyber-physical system, any attack that occurs in the cyber domain is seen in the physical domain, and this is also known as kinetic attacks. There has been various work to highlight this form of attacks. In our attack detection method, we try to create a behavioral model of the system based on analog emissions and try to detect when an attacker would try to sabotage the firmware of the 3D printer. For firmware attacks that change various parameters of the 3D printer, our attack model was able to detect various changes with accuracies as shown in the figure. Moreover, as a real-world test case, we tried to detect attacks that caused minute changes in the third, fourth, and fifth layer of a base plate of a quadcopter. Our attack model was able to detect any changes that was more than 4 mm.